Okay, so we have the Gibbs energy as delta H minus T delta S. And remember that that is just a restatement of the second law. So what we know is that delta G less than 0 means nothing more than delta S of the universe. This is how we defined it. Greater than 0. Okay, they're synonymous. It's just if this is done for constant temperature and pressure, delta G tells us that delta S, delta G decreasing tells us delta S of the universe is increasing or spontaneous. So from this we can now look at the enthalpy term and the entropy term and define 4 types of equation or reaction, I mean, okay, in terms of whether it's exothermic or endothermic and what's happening to the entropy of the system. Okay, so first one would be, let's say we have, we've discussed this before, maybe a negative enthalpy. And I'll remind you, what does that mean? That means it's exothermic. Okay, so it's exothermic, and let's say that the entropy is also positive. Well, you can see now if the enthalpy is negative and the entropy is positive, that second term is just subtracted, delta G is going to be decreasing. So that means that that is always spontaneous. Let me put a title here. The question we're addressing is a reaction spontaneous? Always. What about if we had, again, an exothermic reaction? So it's negative delta H, negative enthalpy, but this time the order of the system, the disorder decreased. You know, maybe you formed a crystal or something like that. Could that ever be spontaneous? Well, we can see, provided the temperature is low enough, that second term is not going to be not going to add too much to the enthalpy, and so we would say it is spontaneous at low temperature. All right. What about if we had now a positive enthalpy, which means it's endothermic? We know that there's some reactions that can be endothermic. In fact, perhaps some examples would help. You know, the first one, exothermic and increasing disorder or increasing entropy. How about combustion of a fuel? Burning fuel. That would certainly be negative enthalpy and positive entropy change. What about freezing H2O, freezing water? Okay, freezing water is actually exothermic, and you know, because it's freezing, it's solidifying, there is a decrease in the entropy, so it is negative. Well, that only happens, you know, at low temperatures. You cool water down enough and it freezes. What about this one, melting ice? Well, melting ice, we know that takes in heat, it's endothermic, but you're breaking up all that order in the crystal, and so it is going to have a positive entropy change, and so that is going to be spontaneous, as you know, if you think about ice, when at high temperatures, right? Because we're getting this contribution from the increase in the entropy. It's allowing it to be spontaneous, allow the entropy of the universe to still increase. And the final thing that you could have would be a positive enthalpy, so again, endothermic, but this time a negative, a decrease in entropy of the system. And when will that be spontaneous? You think of an example. I can't. Why? Because it'll never happen. All right? So those are 4 types of reactions. I think it's really neat to think about them that way, and you can think about both the enthalpy contribution and the entropy contribution contributing to the entropy of the universe through Gibbs energy. And you can really neatly see whether a reaction will proceed or not. Thanks.